Dr. Sezen Sekmen. Dear Professor, welcome. We are very happy to have you today in here.
Thank you very much. I'm happy to be here too.
If you allow me, I want to tell about your success a little bit.
Thank you.
Dr. Sezen Sekmen finished her PhD in the Middle East Technical University, which is one of the most successful universities in Turkey, in 2008. After that, she moved to Florida State University and worked as a researcher at Florida State University in 2009 between 2011. After that, she will move to CERN, Switzerland, which we are talking about today, 2012 to 2014. After Dear Professor, I believe you were a researcher at Formula 2, right?
Yes, that's correct, for 2 years.
That's perfect. Between 2007 and 2008, right?
Yeah.
And you are one of the ambassador of scientists in Turkey, which is, you are still working in a Kyungpook National University at South Korea.
Yes, correct.
For the attendance, dear Professor is one of the most successful professor in Turkey right now, and we are very feeling honored today to have you, Professor. Thank you very much to join us today.
Thank you very much.
We are very happy to see you in here.
Thank you.
Would you like to start?
Yes, sure. So first of all, thank you for inviting me, and thanks for this very nice introduction. I'm flattered. So yes, I've been, working for various institutes, but since almost the last part of my PhD, I had the chance to be based at CERN. So I have been doing all my research at CERN, CMS experiments. So that's, I think, what is the important thing. So today I'm going to tell you a little bit about particle physics and CERN briefly, conceptually, of course, because I know you're a diverse crowd. There are, people from different age groups, different countries. So I try to keep it generic. And I'm happy if you interrupt me with questions. So now what I'm going to do, I will have to turn off my camera because I have to go very close to the computer. So, and I will share my slides. Let's see. I hope it works fine. All right. You see my screen, I hope.
Yes, dear Professor, we can see it.
And then let me make it full screen. All right, it's trying. Yes. Can you see it in full screen mode?
Yes, dear Professor. Yeah.
Okay, thank you. So I will start. Okay, our subject today is particle physics and CERN. So why do we want to learn about particles? Now, it's always important to ask big questions. And actually, people were asking these questions already many years ago. Here's a very nice saying from Plato that goes, the universe cannot be understood without knowing the building blocks of matter. And that is very, very true. And actually, I guess you have all heard about Big Bang, the starting of our universe, right? The Big Bang, according to Big Bang theory, which is almost certain, which is really supported by a lot of experimental evidence, our universe in the beginning of everything was a very, very small point. Actually, everything that is in our universe, all the matter, all the particles, all the galaxies and stars and everything was collected in a very, very small, tiny point, which then exploded and expanded. So in its birth, our universe was a very small point itself. And then what happened? So you can see on the left, the starting point of the universe, the Big Bang. After the Big Bang, as I said, the universe started expanding. And at the early times, the universe was very hot. So in this picture here, you can see several numbers that are below the picture. So you can see the time, how many seconds have passed. You can see the temperature, how hot the universe was. And you can see the corresponding energy density at one single point of the universe. So as you can see, as the universe expanded, it started becoming colder and colder. But in the earliest times, our universe was extremely hot, okay? It was like a hot and dense soup, as we like to say it. And in this hot and dense soup, the particles started to form. So on top of the picture, you can see some names like the CERN LHC, like the FNAL Tevatron, BNL RIC, etc. These are the experiments that we are doing right now in order to observe particles or discover new particles. So, and you have probably seen in the news, yes, they are going to create Big Bang at CERN. So this is a very important thing to clarify. What we are doing is not to create Big Bang at these experiments, because in order to create the Big Bang, you need to have the whole universe together. But what we are doing is to create the energy density that was there at one point of our universe, right after the Big Bang, okay? So when we look at this picture, when we collide particles at the CERN LHC, and we will come to that very shortly, we can go back in time in the universe when the particles first started to become available. They started to be created, okay? So that is a very big connection between understanding particles and understanding our universe. All right, so next slide. Now, we now established that working on particle physics is very important. Understanding particles is very important. But what is particle physics? We should always try to make definitions and understand what we are talking about. Particle physics is an area of research that investigates two things. First of all, we investigate the fundamental particles that make up all the matter that is in our universe. So the you, me, tables, chairs, stars, galaxies, trees, birds, everything, okay? So this is the matter. But that's not all of the story. Particle physics also investigates how these matter particles interact with each other, okay? These matter particles can interact differently in different ways with each other. So different particles can interact to form trees or houses, or they can interact to form chemical reactions, or they can interact via gravity. These are different ways. So we also investigate. Particle physics also investigates these interactions. And actually, the history is quite long. Yes, now we are talking about the big experiments, etc. But people, since hundreds of years, they have been trying to understand the building blocks of matter and figure out how to systematically put them together, list them. And this is something that you see on the right, lower right corner, the periodic table as we know today. But we know that it wasn't always like that. So the one at the top right corner, the primitive looking table, was actually the first version of Mendeleev. So we keep improving on our knowledge and we keep trying to go towards the more fundamental particles. Okay, but the periodic table, of course, was all about the atoms. And even when the periodic table was done, we did have some sort of an idea that these atoms in the periodic table were not actually the fundamental particles. So the quest continued. And actually, the big breakthroughs came in the 20th century, in the beginning of the 20th century. So, well, I guess most of you are more or less familiar with this story. So the journey inside the atom, it starts with the discovery of the electron by J.J. Thomson in 1897. And then, so this was the very first thing, the very first subatomic particle that humankind has discovered, the electron. But that wasn't all. So we were thinking, okay, there's the electron, some negatively charged particle in the atom, and then these negatively charged particles were embedded in some big plum pudding kind of thing. But it turned out soon after, thanks to Rutherford's experiments, that it wasn't that way. Actually, the electron were very tiny particles which were surrounding or which were going around the nucleus of the atom. And this nucleus was a very, very dense thing that was at the center of the atom, just like our solar system and the sun. Then soon after, it was understood that the nucleus itself was not an elementary particle, but there were protons and neutrons inside the nucleus. So again, people were saying, okay, how much further can we go down? Then people did further experiments, and the quarks were discovered. So far, quarks are the final, let's say, frontier when we go deep into the atom. But okay, this is a very simple picture when we look at the atom, and it's definitely not the whole story. Because in the 1930s and 40s, when people were going down the atom, examining the atoms, other people were looking at the cosmic particles, the particles that come to our Earth from the universe, okay? So, and in these cosmic particles, people started to discover some very weird elementary or very weird particles, let's say, which were not familiar to us, which were not like any of the particles that are in our atoms. For example, they discovered positrons, which are positively charged electrons. They discovered muons, which were like electrons but heavier. Then they described neutrinos, which was really weird because these particles were ghosts and we didn't observe them directly anyway. We just indirectly figured out their existence. Then we discovered tons and tons of particles that people called mesons, people and later on baryons, let's say, and people couldn't make any sense of them because, well, the idea was to look for elementary particles, but when you think of elementary particles, let's imagine we are looking for an alphabet, right? So for example, we found, I don't know, we went to a different planet, let's say, and then we found some writing somewhere and we are trying to figure out what language it is, right? We automatically imagine that there's an alphabet that is made of certain amount of letters, I don't know, 30, 40, maybe 20 letters. But when you start discovering hundreds of letters, you try to think, wait a moment, these cannot be fundamental letters, I'm making a mistake. So people were quite confused by all these experimental discoveries and they didn't know what to do. Things weren't simple anymore. So there were a lot of particles going around and they didn't know what to do with these particles. But happily, theorists came along and then they made all this understanding into a model. We are going to come to that. But before that, let's go back for a moment to the second thing that the particle physics deals with, which is the fundamental interactions. So we said particle physics deals with matter and it also deals with interactions. Nowadays, we know for certain that different matter particles interact by other particles or via other particles, via exchanging other particles. So we are going to come to which kinds of forces there are in the nature in the next slide, but it's important to understand that when we are talking about two matter particles interacting with each other or applying a force on each other, that force is carried between these matter particles by some interaction particles or force carrier particles. And I think, the best way to describe this, as you see here in the picture, is like a tennis match, right? You have the two players, which can be thought of as matter particles, and you have the tennis ball, which is somehow like the interaction particle. The first guy hits the ball, and then the second guy feels the force with the ball, right? Of course, it's really like a very crude analogy, but I hope you can understand what I'm trying to say here. Right. So while people were discovering the matter and other physicists were thinking about how the interactions were done, and they were understanding that in interactions or forces are transmitted between particles via dedicated force carrier particles. Okay. Now, what are the fundamental forces in the universe? So far, we know 4 fundamental forces in the universe. The first one is very familiar to all of us. It's the electromagnetic force. So it's all about electricity, magnetism. It's holding electrons together with the nucleus, making atoms, and it's binding atoms atoms to molecules, and it's responsible of all chemical reactions, etc., etc. This is very familiar. So that is one fundamental force. The other one, strong force, is much less familiar, but it's extremely important. This is the force that makes up the protons and neutrons that are at the center of the atoms. So as we briefly saw, protons and neutrons are made of quarks, but what puts these quarks together? It is the strong force that puts these quarks together and builds protons and neutrons and other particles that we just discussed, which are called mesons and baryons. So, okay, we have the electromagnetic force, we have the strong force. Then we have another force that's called the weak force. That was even less familiar with people, but it's really very important because this is the force to what we owe all our lives, because this is the force that's responsible of radioactivity, and it causes the nuclear reactions at the center of our sun. So it's literally the energy source that comes to our Earth and that makes life possible. So it's very important. Then finally, the gravitational force. I guess it requires no explaining. Everyone knows about Newton and Apple, and everyone knows that all matter actually attracts all other matter, literally. So it's not only about the gravity of the Earth. It's not only about the Earth pulling the apple. The important thing to remember here is that the apple also pulls the Earth. So whenever you have some matter, it pulls all other matter within its reach. All right, now we talked about particles. I tried to give you a very brief historical review, very, very fast. I hope you could get something out of it. And we talked about interactions, and we talked about the importance of getting all this information and arranging it in a nice way. Okay, so that's what the physicists were trying to do in 1960s and 1970s. So in some place, the experimentalists were trying to discover and measure particles, and on the other side, the theorists were trying to get that information and put all that information in a coherent theory that would host all the experimental observations that were made by experiments up to that time. So all that knowledge, all that information was collected into a group of theories which we call the standard model of particle physics. So these theories, well, when you look at them mathematically, they're of course very, very complex. You need to have a lot of very deep understanding, fundamental understanding of quantum mechanics, and then field theory, and then quantum field theory, etc., etc. So it really builds up all this information. But the idea, as I can present it here, is quite simple. So we do have a certain amount of fundamental particles. So even though we were observing all sorts of different particles, it's just like in the case of atoms and molecules, or molecules to atoms. So we do have some combinations of fundamental particles which we observe, but in the end, they all boil down to a table of several well understood and well listed, well measured fundamental particles. And this is what you see here. So you see all the fundamental particles that we know in this picture. And it's actually not a very big list. So let me actually stop here and ask, how is it going? Am I going too fast? Is it too difficult, too easy? Can someone tell me something?
So clear, our teacher, and we are listening.
Okay.
With understanding, thank you.
Okay. So again, I ask you, if you have any questions, please ask. I'm not following the participants window, so I'll leave it to the chair to, to the organizers to give word if someone has.
Dear Professor, actually we took a lot of questions right now, but we have to do a question answer session after your presentation. That's why no one answer you right now.
Oh, okay, fine. But okay, that's fine. That's fine with me. It's just that if there's something people don't understand that I'm saying, then
we totally understand you, but you really shocked us with that information, that news things. That's why everyone quiet right now. Thank you very much.
Okay, fine. So anyway, well, you know when to tell if something's too difficult, etc. Anyway, now I go back to physics. Fine. So this is standard model as you see it. So let's try to understand what's going on here. So in this table we have the matter particles. Forget about fermions and bosons. This is just terminology. You don't need to care about that. We have the matter particles on the left, and we have the interaction particles on the right. Okay. So again, we know that interactions are also done with via particles. And then we have the Higgs particle. I'm sure everyone knows about the Higgs particle, at least about its name, right? The God particle, Higgs particle, whatever. So it's a different thing. I'll tell you about that. Now, there are different types of matter particles. So you see the green ones, the leptons, and then you see the pink ones, the quarks, the ones on the top. And then in the leptons, you see electrons, muons, and tau, the first line, let's say, the first green line. And then you see the neutrinos, right? Electron neutrino, muon neutrino, and tau neutrino. Now the question is, why do we have all these kinds of different fundamental particles? The answer, we don't know.
Yes.
I mean, we don't know why, what was the purpose, what was the reason, but we know how they are used or what they are used for, or what is it that makes it different from each other, okay? What is it that makes a quark different from a lepton? And the answer is actually very simple. All these particles interact differently, okay? Interact with different particles. So when we look at the gluons here, okay, actually, let me step back, just step back for one moment. Let's also go through the interaction particles before we make the connection. So we looked at leptons and quarks on the left. These are the matter particles, right? And then we have quarks, we have the leptons with electron charge, and then we have the neutral leptons with zero electric charge, the neutrinos, okay? Then we go back to the interaction particles, the tennis ball particles, they are transmitting the interactions between matter particles. And again, let's remember the different types of forces. We were talking about the electromagnetic interaction, right? So the electromagnetic interaction needs to have one particle that transmits it. And that particle is the photon, the one in the middle. Right? So you can read the names, I hope. Okay. And then we had another interaction, the strong interaction. So the particle that transmits strong interaction is the gluon, which is on the top. All right. And then finally, we had the weak interactions. And the particles that transmit this kind of interaction are the W and the Z particles. They are at the bottom. Then you may be asking, what happened to gravity? Actually, the standard model cannot describe gravity right now. Okay, that's a question for tomorrow, let's say, or 20 years later. We can only explain these three forces using our theoretical knowledge, okay, via particles. So now that I introduce you the interaction particles, we can go back to the standard model. So what happens is that different matter particles interact with different interactions. When we go to let's start from the bottom. When we go to the neutrinos, the ones at the very bottom, they can only interact with weak interactions, with W and Z bosons. Okay. When you go up, the electron muon and tau leptons, they can interact with both electromagnetic interactions with photon and also with W and Z particles. Now, we go back to the quarks, to the top. We are going towards the top. The quarks, they can interact with all three interactions, with strong, with electromagnetic, and with weak. Okay. So, as I was saying, matter particles can interact differently, and the way that interact allows to classify the different matter particles. So that's how we sort of do the accounting of standard model particles. All right. So that's what we know about the current particles that are around, wandering around in our universe. But of course, this is not the end of the story. The standard model is correct. As I said, standard model has been observed by the experiments. All these particles that you see were observed by the experiments. However, it's incomplete. There are several things that the standard model cannot explain. And how can I say this? I mean, you can say, how can a theory be both correct and incomplete? Well, there you see the answer, right? When you're in this room, you are looking outside, or you're looking at the limited perspective, you see that the Earth is flat, right? No one can argue that. It really looks flat. This is correct. This is not wrong. But you just need to go up to the space, or go really high up, go in an airplane, etc., and observe the curvature of the Earth. And then you can say that the Earth is round. So that's what we need to do. We must extend our point of view. We just want to go up a little bit and see what could be a more generic theory that includes the standard model, but that adds more stuff, or more particles, or more theories on top of it, so that the new theory can explain the universe in a better way, right? Just like the round Earth hypothesis explains the reality better than the flat Earth hypothesis. And in order to do this, we have to get help from the stuff that the standard model cannot explain. Okay, so the deficiencies are not actually bad things, they are good things. Okay, now let's try to go through some of these deficiencies and how we are approaching them, how we are trying to find answers to them. So one deficiency is the problem of mass. I mean, maybe you noticed in that standard model table, there were masses of the particles written. It's not important if you didn't, but here's a better picture of the masses. So all of these particles that you see, they have very different masses. Some of them are very light, and some of them are really very heavy. And we don't know why. This really looks random to us. Why could this be? Why could different particles have different masses? Okay, but there's even a more fundamental question when you are talking about this. You can ask, well, why different particles have different mass? But wait a moment, what is mass? What do you mean by mass? Why does a particle even have mass, right? So this is a very interesting question to ask and try to answer. And people were, of course, trying to answer this question, and that is where the Higgs boson, or Higgs mechanism, or Higgs particle, all the Higgs story comes in. So the Higgs mechanism, or the theory called the Higgs mechanism, is the answer to this question. Again, this is a very complicated mathematical theory, and we by no means are going to go into that. But I can tell you very, very briefly what happens. There is a field, or there's a field called Higgs field in our universe. Okay, now we stop again. You might be asking, what the hell is a field, right? It's a field. It's an abstract thing, but you can, well, the easiest way to imagine could be maybe like an electric field. You've heard about an electric field, right? Or a magnetic field. So you put all these iron fillings on a paper, you put two magnets, and then the magnets somehow align in lines. So that's a field, right? The invisible thing that makes all the iron fillings align with the magnetic field. Okay. Or if you don't want to think about that, you can just imagine the universe like a big swimming pool or a big ocean full of water, and that water is the field. It's just that some entity that exists in a space and time, and it can have very variable, let's say, results or quantities in every point in space-time. That's a field. Now, coming back to the Higgs. The Higgs idea is that there's a field, a Higgs field in the universe, just like an ocean, in all universe. And then different particles that we know somehow interact with these fields, just like with different swimmers, interacting differently with the sea, right? So you might have a very good swimmer who can swim very fast, or you might have a very bad swimmer who can swim very slowly and very badly, and who actually sinks, right? Or you could have a very light, small kid swimming only 20, 30 kilos and can swim very swift and fast. And you can have a very heavy adult, like 150 kilos, swimming very difficult way, or splashing a lot of water, right? You can imagine like that. So indeed, the particles interact with this Higgs field in a different way. And the stronger they interact, like our big adult with 150 kilos, the heavier they are. Okay, this is all I can say. Now, the more will require us to be here for 2 more hours, at least. Okay, so particles interact with this Higgs field. If they interact, they gain mass. And the more they interact with the field, the more they get mass. That's the idea. So that is what describes mass, the existence of mass, and how different particles have different masses. Now, what does all of this have to do with CERN and the big experiment, the Large Hadron Collider there? If this Higgs field exists, if this theory is correct, there needs to be a particle called the Higgs particle. And we should be able to observe this Higgs particle in an experiment. That's the story. So it's really, there's a Higgs field, it explains mass. If the Higgs field is there, there's a Higgs particle. If the Higgs particle is there, we should be able to produce it, and we should be able to observe it. Okay, that's the reasoning, that's the line of thought. And now the question is, how do we observe the Higgs particle, the Higgs boson? How do we see it? And the answer is actually has 2 sides to it. First of all, we need to produce this particle, because in a controlled way. I mean, this particle is produced maybe in the universe here and there, but we don't know where it is. So the best way to see it is to make it for yourself, right? And how do we make it, actually? Now, this brings us to the principle of all these experiments at CERN. The idea is going back to Einstein. It's simply E equals to mc squared, okay? I guess everyone here has heard of this formula. E is energy, m is mass, and c is the speed of light. So what happens is we collide particles, protons in our case, and in the case of current CERN experiment, we take protons and we collide them, like you see in the picture. We collide them very fast with very high energies. And then these energies they correspond to the mass of the Higgs particle. So after this collision, we are able to make a Higgs particle. And for that, the instrument that we need is a particle accelerator that is built, that exists at CERN. I'm going to show you pictures just shortly. But that's not all of the story. It's not like, okay, we made the Higgs particle, now let's take its photograph. It's not that easy. Why? Because the Higgs particle is not stable. It decays to smaller particles, okay? And it can decay in many, many different ways, let's say. But here, I'm only showing an example. It decays to the particles that we know from standard model. So you can maybe recognize the Z particles, right? The interaction, the force carriers of weak charge. And which in turn decay to other particles. And in this case, these are leptons. They can be electrons, muons, taus, etc. It doesn't matter. Well, the thing to keep or remember here from here is that the Higgs particle is not stable. It decays to standard model particles, or particles we know, like the light particles we know from the standard model. Now the task becomes to observe these particles, to take their photographs, literally. And the devices that we use for taking the photographs, of course, these are digital electronic photographs, not like pictures, and never mind. But the idea is the same. We are taking photographs, we are collecting these signals. These instruments are called particle detectors. And I'm sure you heard of CMS, Atlas, in the news. So CMS and Atlas, these are the particle detectors that take the pictures, the photos of the particles once they are produced. All right, maybe enough of physics for now. Let's just go to CERN for a moment. So all these things, all this physics research is done in several places around the world, but of course, undeniably, CERN is the biggest of these research centers currently. So it's the name stands for European Organization for Nuclear Research. Nuclear is just historical. We are not doing any nuclear bombs or anything like that. It's actually should be particle research. And this is, well, CERN is literally a high energy physics laboratory. It's at Swiss-French border and it's in Geneva. And its complete purpose is to investigate the nature of fundamental particles and interaction. So it's a scientific laboratory. So it has, let's say, more than 12,000 researchers from 608 universities from 113 nations. So it's really, really global. And one thing I can proudly say that it is the place where the World Wide Web was born. And what are the goals of this place? Of course, we want to push the boundaries of knowledge. You know, we want to discover the Higgs boson or other particles, other new particles. And we want to extend our understanding of physics. And CERN also wants to invent and develop accelerator and detector technologies so we can produce new particles and we can observe new particles. That's quite important. Then CERN also wants to educate the scientists and engineers of tomorrow. So education is a very big part of CERN's goals, because the better educated we are, the better physics we produce, right? And also, well, we should note that it's a very international place, so it's bringing people from different countries, different cultures, etc., to create a very productive and interesting scientific heritage and working atmosphere. Now, the most important experiment at CERN, we said that CERN is a laboratory, of course, and it is a very complex organization. So it's a laboratory, but it has many different experiments, and it has theorists in it, and it has engineers, etc. So it's not like one thing. It has multiple ongoing activities inside. But anyway, the biggest experiment that's ongoing is the Large Hadron Collider, whose name I guess everyone has heard. So the Large Hadron Collider is an accelerator. I'll just show you some pictures. And then here you see in the different points, there are several detectors that detect the particles, observe, and take their photographs and collect data. Now, the Large Hadron Collider is quite fascinating, actually. It's an amazing experiment. It's maybe the most complex machine built by the humanity. So it is the accelerator with the highest energy so far, 14 tera-electron volt. And it's 100 meters underground, and it has a circumference of 27 kilometers. Then, coming to the detectors are the largest and the most complicated ones that were ever built. Okay. Then, of course, well, since we are talking about a lot of data, a lot of information, we need to collect this information, and we need very sophisticated computer systems. So we have the world's most extensive supercomputing system. But then there are also some interesting and fun facts. Some collisions at the LHC, they generate temperatures that are almost 100,000 times hotter than the center of the sun. So this is really not a joke. Another thing, inside the accelerator, we need to have very cold temperatures in order to have very strong magnets that produce these proton beams that are colliding. And this requires superconducting magnets, superconductor technology. And in order to operate that technology, we need to have 1.9 Kelvin, which is literally colder than the outer space. And finally, in this accelerator, since we have beams that are made of a lot of protons that are ongoing, in order to have these beams nicely traveling, we need to have a vacuum. So the vacuum inside the LHC tunnel is as empty as the interplanetary space. So it's really a crazy empty vacuum. Okay. So the LHC is indeed, and its detectors, they are really the ultimate when it comes to experimentation. Now, this is how things look. So as we said, there's the LHC tunnel, and then we have the detectors around there. So here you can see the Atlas detector, for example. So you have the accelerator pipe, and then you have a detector that is about 100 meters below the ground. And then particles come and collide in this detector, and they make Higgs particles or whatever other particles. Is there a question or something? Okay.
Professor, if you finish, yeah, we can move to the question and answer session.
No, I still would like to show a few things. Okay, so this is how a detector looks like. This is the Atlas detector where the collisions happen. Okay. And actually, maybe let me ask. So how much time do we have? We started around 25 past, maybe?
It doesn't matter. You might feel free because you got time, Professor. When you finish, you can finish.
Okay. So maybe I talk for like 10, 15 more minutes and then we go to the question.
Please be free. Please be free.
Okay, fine. Because I really don't want to take up time. Okay. So these detectors, I mean, you've seen in the slide before, you see that these detectors are extremely complex structures, right? Also in the newspaper, you see these really fancy pictures. Why are these detectors so complex? The idea, well, the answer is because these detectors are designed to measure different particles, okay? So they are like onions made out of layers from different materials. And all sorts of particles, as you can see in this picture here, they interact differently with each layer of the detector. So if you have an electron, it interacts differently. If you have a photon, it interacts differently. If you have a muon, it interacts differently. So it's really like a puzzle We look at the different layers in a detector, and then we collect all this information from different layers, and we put it together just like a puzzle, and we try to understand what particle has passed through and made these marks, right? It's just like, you know, looking at some footprints, and you try to figure out whether it was a, you know, polar bear or it was a little nice dog. It's really like that. So, okay, we have the collisions which happened in our accelerator, and then we have the decays, and then we have the different particles, and the different particles pass through our detector. And we looked at the marks that they made in our detector, and we understood which particles they were. Were they electrons? Were they muons, etc.? And we can get this information. We can display this information like in the picture you are seeing here, right? This is like the detector, the cylinder is the detector, and all these different lines you are seeing here correspond to different particles. For example, the red ones correspond to muons, particles that are called muons, and the green single lines, they correspond to particles that are called electrons, okay? So we can actually look at these pictures, well, or rather numbers, and try to figure out what has happened after a particle collision. But looking at all these pictures one by one is an extremely difficult thing, because we have so many collisions, millions and millions, hundreds of millions of collisions happening. So what do? We try to put this information together in a meaningful way. So we produce some graphics, like this one here. It's actually, you know, again, it will take me a while to explain all that is happening here, but it's just enough for you to understand the main idea. So the black dots here are the data, and each data corresponds to one collision event, like the one we just saw in the picture. And then we are trying to figure out with which theory our data is consistent. Is it consistent with the Higgs, or is it consistent with no Higgs? And actually, we do have some simulation tools, let's say, that can tell us how different theories would look like. So we can make computer simulations. I guess you understand what this means. Not the real thing, but just like we have, you know, computers simulated animated movies rather than real people, we can do the same for collision events. And we can simulate how the Higgs particle would look like in our data, and how the case without the Higgs particle would look like in our data. And then what we do in the end, in the simplest sense, is to compare our data with the different theory predictions. And then we see, okay, is our data agreeing with Higgs, or is our data agreeing with something else? So if you look at this picture, our data is obviously agreeing with the Higgs, right? The black dots are agreeing with the red little peak there. So by looking at plots like this, we can say that we discovered the Higgs particle. And of course, the Higgs particle led to a Nobel Prize in physics, and it's very important, etc. So now I'm going to skip this, and I'm just going to say a few more words before I finish. So the problem of mass was a very important problem in the past 60 years or so. And now we can say that it is solved, because CERN has discovered the Higgs boson. And now the Higgs boson, or the Higgs particle, has become a part of the standard model. But this is not the end of the story. Okay, the standard model with the Higgs particle still explains a lot, but there are still a lot of questions, a lot of deficiencies that are left in the standard model. So I'm just going to very quickly go through this a little bit in the final part of the talk. So several questions. Why do we have different families of particles? So you can see first family, second family, third family. Okay, so the atoms that make us, they are made of only the first family, the electron, and then the up and the down quarks. But why do we need the other families? Why do we need the second and third family? So this is an important question, and we don't know the answer. Now, another question was one we mentioned briefly. There are the electromagnetic weak and strong forces. So these forces can be explained by the standard model, but the gravity, the one that's most familiar to us, it cannot be explained by the standard model. Why? So what is a theory to explain gravity? We don't know about that. All right? Now, another thing, we know that there's something called a matter-antimatter asymmetry in the universe. Well, I guess you are all curious about antimatter. We can discuss it later. But due to some sort of asymmetry, let me not go into detail, we exist. So we are existing accidentally. If the standard model was the only model that's around, none of us would be existing in the universe. So we need some other thing to break the symmetry between matter and antimatter in the universe so that there's much more matter than antimatter. And all that matter makes up the galaxies and the planets and the plants and us and everything. Okay? And we don't know the answer to that. And it's not all. So the matter that we know is only making about 4 to 5% of the universe. The rest, 95% of the universe is made of things called dark matter and dark energy. And we have no idea what these things are. You know, we do have guesses, we do have some theories for explaining them, but we have zero experimental evidence about dark matter or dark energy. So we don't know what they are made of. I'm going to skip this. And yeah, so these are some of the questions. There are more questions, and these questions are more technical, so I'm not going to talk about this. But I'm just going to say what we are doing right now to find answers to these questions and go to the next fundamental theory after the standard model. So we can do two things. We either make a surprise experimental observation that is inconsistent with the standard model. So for example, we know the electron's mass. We measure an electron that is much heavier than the ones that we know. That's a surprise, right? That's unexpected. So then we try to make up a theory that explains this weirdness, right? Strangeness. That is one way. And what's the second way? The second way is to look at standard models' deficiencies or the questions and postulate new theories that may find answers to these questions. You know, dark matter, for example. Okay, there should be dark matter in the universe. We know this indirectly. What could dark matter be made of? Maybe dark matter is made of some particles. How could these particles be? How heavy could they be? Right? So you ask these kinds of questions and then you try to make theories. That's what all our theorist friends are doing. But the important thing is to be able to observe the predictions by these theories. So if my theorist friend is making a theory for dark matter and she says that there are some, I don't know, particles, like X particles, and they have a certain mass, I just need to be able to observe them in my experiment before we can say that her theory is true, right? So experiment is extremely important. Okay, this brings me really to my last slide. So LHC, as I said, is like the ultimate experiment, particle physics experiment right now, who is trying to find new particles and make measurements, etc. And Of course, it's not the only experiment. There are many other experiments, but as I say, it's the biggest and with the highest energy. So it's the closest to experiment with highest probability of making a discovery. So what is happening at the LHC and what is going to happen at the LHC next? So you can see in this picture sort of a timeline. It's a little small, I know, but there's nothing I can do. So you can see the years in the blue strip in the middle. LHC started taking proper data, physics data, in 2010. And since then, it has been collecting a lot of data in different collision energies. So the green dotted line shows today, actually. Up to today, LHC has collected data, but not always. Sometimes it was stopped in order to improve the detectors, improve the accelerators, so we call them upgrades. And as the data was being collected, of course, physicists like myself, we analyzed all that data in many, many different ways, hundreds of ways. So it's not like there's one data set and you do one analysis. No, you have the data set and you have to look at it from hundreds of different ways in order to figure out if there are any new particles. Of course, the Higgs particle was discovered in 2012, and then afterwards it was thoroughly measured. There were a lot of measurements done on the particle, but as I said, a lot of other analyses are ongoing. And unfortunately, so far, apart from the Higgs particle, there are no hints for new particles beyond the standard model. So the only thing we've discovered at the LHC so far is the Higgs particle. But we have looked at a lot of places and we can say, okay, there is no particle with this mass here. There's no particle, heavy particle that was predicted by this theory. So we can exclude or invalidate a lot of theories by looking at the data. So we can say what is not there, but yet we cannot say what is there. Maybe tomorrow. But of course, we never give up. At this point, the experiment is not working. It's not collecting data because it is preparing for the next phase. So our detectors are being improved. It's again an upgrade phase. So we are going to start taking data, as you can see, in the beginning of next year, hopefully, for a while. And then we will stop for a long while, for about 3 years, for a very big upgrade project. And then the LHC will become a much, much stronger experiment. So it will allow us to collect 10 times more data and with a higher energy. So this data will allow us to look at much, much deeper places, explore a lot of more theories and look for many more experimental signs, let's say. So we are not giving up and we will continue searching until probably the end of 2030s. And who knows, maybe some of you will join us in the search. Okay, I'm done for now. Thank you. Now questions.
Dear Professor, can you hear me right now?
Yes.
Okay. Dear Professor, that's really wonderful presentation. First, thank you very much. Thank you very much. Now, I will take the questions one by one. But the questions in the Filiz teachers right now, I think. So Filiz teacher, can you send me the WhatsApp questions that the students sent you before?
Okay, I'm sending you now, my teacher. The first question has come.
Okay.
I will send one by one, my teacher.
Okay, dear Professor, I'm asking your first question, and this will how will CERN contribute to world civilization in the future?
Very good. Okay, now I'm also, I turned on my camera. Actually, you can see a picture of LHC tunnel.
Professor, if you want, you can stop your screen sharing and everyone can see you.
Okay.
If you want.
Yeah, just in case I had to show slides, but okay. fine. I stopped the screen sharing. Well, how will CERN contribute to civilization? CERN has already contributed to civilization in the past. With technology, well, first of all, science. CERN contributes to civilization by doing science. Science is extremely important for civilization because it's what makes us human. You know, it's what makes it worth living, you know, knowledge, moving forward, understanding the universe, you know, recognizing our place. These are extremely important. And CERN is doing this as I said, in an international way, you know, just like we are coming from different countries here. Well, more than 100 countries, so many different cultures. It's really quite challenging and interesting to work there. So it's, in a sense, contributing to peace and understanding. But if you think that these things are blah blah, and you know, they are not important, now let's come to technology. So CERN is inventing frontier technology in order to build these big accelerators and detectors. For example, particle accelerators and detectors, above all, they are used in medical sciences. They are used in cancer therapy. They are used in medical imaging. They are used in clean energy. They are used in cleaning the environment, actually, even, you know, getting rid of the bad gases in the atmosphere and converting them to fertilizers, even that. So accelerators and detectors have enormous technological uses for the society. They are used for making rubber. I mean, I can count so many things. Therefore, all the technology that are being developed at CERN for fundamental research purposes do have technological uses and advantages, which are continuously being explored by engineers and different companies, you know, which cooperate with CERN. And another thing is the computing era. So as I said, World Wide Web, right? What's a bigger contribution to civilization? That was discovered at CERN because Tim Berners-Lee, who was working at CERN, wanted a good way to store and share data. So he invented World Wide Web, and he gave it for free to humanity. He's not getting a single, you know, dollar or euro, franc, whatever, for that invention. Yeah. So next question.
Of course, I'm asking you another question. Professor, thank you very much for your request. Let's say I have two, that questions came from the Kazakhstan, by the way. Let's say I have two entangled atoms, and these are the distant each other. Mm-hmm. We know atoms act different in different temperatures. They have a higher energies in a higher temperatures and vibrate faster. So if I cool one of these atoms, the other atom would act like it's in cold too. They talk about the definition of the atoms, you know. There is two atoms, and if I would make it hotter, and if I make it the other ones colder, which one will be hotter?
Well, simple answer is I don't know. Yeah, it's not particle physics research, frankly. It's more related to quantum theory research, or that area. So it's unrelated to CERN work. And therefore I don't know the answer. So I'm sorry. Probably ask a quantum physicist. Sorry. Yeah.
Okay, I'm moving the other question. According to Michio, today humans have completely theoretical knowledge about time travel, and that time travel now is only an engineering problem. What do you think about this question?
Well, I think it's still a theory. Well, I thought I made it quite clear. Without experimental proof, it's just a theory.
Okay. The other question is, if the experiment is successful and we have the first states of universe, what are the most important technological development that will come into us?
That's a good question. So, well, there are two types of technological developments. One technological development type is the one that comes by developing the experiments, making the experimental setup, building the accelerators and detectors. And we already talked about that. This is already, injected to society, and it's going to be injected even further. As we make advances in technology, things are going to go to society. But the other thing comes with the discovery, right? So the other technological advancement, the second class, is related to the particles that we discover at the LHC. And so far, we only discovered the Higgs particle and nothing else yet, okay? So by looking at the Higgs particle, no one can yet predict how it will be used technologically, because remember, the Higgs particle is discovered, but it decays immediately, much less than a second. Before a second passes, the Higgs particle is not there. So we can currently only take its photograph. We cannot do anything about it. We can make it and we can take its photograph. That's it. We don't know how to use it. But again, I must go back 100 years ago to this very famous thing with Faraday, I'm thinking. So they came to his lab from the government, and he was working with electrons, and then they asked him, what is this going to be useful? And he said, I don't know right now, but I'm sure your government will find a way to take taxes from it in several years. And we all pay for electricity bills, right? So we don't know. Again, we know what may come up from the experimental, let's say, development, the instrumentation development, but we don't know how we can use the Higgs boson to develop technologies. So that's up to you guys to figure out. We are too old. You're the next generation. It's your job. Okay. Next.
You heard it, guys. So you know what to
work
do.
Hard.
You know what to do right now.
Yes, I'm gonna retire. So
Okay. Mrs. Pasupati from Malaysia asked, is it possible to stop a particle from moving at all?
Stop a particle?
Yes.
Wow. Yes.
From moving at all.
So it depends on what particle you are talking about. If you are talking about the photon, a massless particle, you cannot stop it. If you are talking about an electron, yes, you can stop it. Actually, that's how we do our measurements, by stopping particles. The way of stopping a particle is to absorb its energy, actually. And that's how the particle detectors work. I mean, maybe you remember I showed the passage of different particles through a slice of a detector, and there are different layers I mentioned in those detectors to measure different types of particles. So it's really like there's a car. I mean, you've seen it in the movies, right? There's a very fast car going, and then the car goes into the shops, etc., and that's how it stops. It's literally what we are doing with the detectors, right? We are just stopping the particle, and then we are measuring the energy that the particle gives away when we are trying to stop it, and that's how we can see the particle in the detector. So yes, the answer is yes, but you cannot stop a photon in the empty universe. It's not gonna stop because it has to go at light speed. Okay, next question.
Okay. Okay, that question is coming from, Neptune Yilmaz. It's a Turkish student. Dear Sekmen, I'm curious about the dark matter. We know that that there must be dark matter according to the observed rotational velocity of stars, which are near to the galaxy center. Why we can't see the effect of dark matter in our solar system? Is it possible for us to be much heavier than we measured? Also, is there any interaction between neutrinos and dark matter particles?
Oh, very advanced question. Thank you. And by the way, I received your email. I will reply to you. Yes, so first question, we cannot, again, dark matter and the solar system, you have to ask this to astrophysicists. Again, I'm a particle physicist, but the reason I can say very briefly is we cannot observe this because indeed it's not a significant effect. So as you say, the rotation curves are measured in the galaxies where there are a lot of matter. And the matter that we have in our solar system is so small, we cannot measure it. It's, we don't have the devices with sufficient refinement to measure. Now, the second question, neutrinos. Neutrinos were considered as a part of dark matter, but in the end, people decided that neutrinos cannot make up the dark matter. And the reason is because neutrinos are, first of all, too light. They're almost massless. In order to make dark matter, you need to have, well, if the dark matter consists of particles, those particles need to be heavy, much heavier than neutrinos, in order to make up for their percentage in the universe. But that's not all of the story. The second part, the neutrinos, due to their nature, they are going very, very fast in the universe. So they're going almost with the speed of light. And that's no good, okay? If you're going too fast, you cannot settle down in the universe and you cannot cool down in order to make the dark matter. So neutrinos may constitute a very small part of dark matter, but they are not capable of accounting for all of the dark matter.
Okay.
I have one question. Can I ask?
Yeah, you may ask your question, of course.
Actually, I have one concern and one question. I'm Ajmal from Sri Lanka.
Okay.
Professor, when I was studying undergraduate study in 2016, I applied for the CERN internship. There was a program, CERN summer internship program. So I was concerned, like I applied and rejected 2 times because they are giving only for the certain countries like Commonwealth countries and some other countries, but not Sri Lanka is not included at all, and that's the reason I was rejected. And that was one of my concern. If you can like include us also, that will be great help for Sri Lankan students. Now I'm pursuing PhD in Australian University in the field of biomedical engineering. Actually, I had one small question, like it was asked from one of my students. So he was asking, like when we break, let's say when we break certain particles, we can join it together. But when we break certain particles, we cannot join it together. Let's say when we broke a stick, we cannot join as it was. So what was the reason behind that?
Well, okay. Maybe first of all, your second question, I am not sure I understood. What you are saying is making a state of particles and breaking a state. So what state, are you talking about quantum states, or are you talking about experimentally building new particles? What is the exact question?
Not experimental. Let's say like when we have a glass of water and we separated it to 2 glass of water, and if we combine that will be together as it was. But when we broke a stick or can into 2 parts, and if we cannot stick it together before as it was, that was the question I got.
Well, I mean, okay, so this really depends on which particles you are considering. So as I shown you, standard model has many particles, and these particles interact in certain ways, and maybe you can search for so-called Feynman diagrams in order to look at these interactions. So many of these interactions have happen according to some rules, you know, energy conservation, mass conservation, etc., etc. So some of these interactions, because of these rules, they can happen only one way, but they cannot happen the other way around. And why? Well, why it was made like that, I don't know. It's just like a child is born, the child goes out of the mother, but you cannot put the child back into the mother because, you know, it's energy inefficient, right? You have to spend a lot of energy. So the universe chooses to be, let's say, economical in the interactions. Well, maybe that is your answer. The difficult reverse interactions cannot happen because they are less economic than the main interaction that is going forward. Now, coming to your first question, well, first of all, I'm not working for, I work at CERN, but I'm not working for CERN, and I'm Turkish, and just like you, I come from a, let's say, country which is not a member state. So the same problems apply to us. What I can say is CERN does not distinguish, well, of course, CERN always does a priority for its member state countries because they pay money, right? CERN needs money and member states pay money. So that's why people from member states like Germany or places like America, Italy, etc., they have priority when they apply. However, and Turkey is not also a member state, let me tell you. However, in internship programs, summer student programs, etc., a lot of people from non-member states apply. And these people also get accepted. For example, I worked with a student from Bangladesh. I worked with another student from Madagascar last year. So these things happen. But the problem is it's extremely competitive, okay? Thousands of people apply. Thousands and thousands of people apply, and then only 100 people get accepted. So it's a matter of statistics. And coming from a non-member state country, unfortunately, you are disadvantaged. But I am almost as disadvantaged as you, and I'm also having similar kind of problems in continuing my research here, even as a more senior researcher. Okay, so unfortunately, that's the way of life.
Thank you very much, Professor.
Sure. Yeah. Next question.
Oh my God, I'm asking question to myself because I forgot.
Yeah.
I'm sorry, Professor. I'm sorry.
No problem.
Actually, one of our teacher, Mrs. Kaya, which is working as my colleague, is a physics teacher in my college, ask a question: is any development of particles affect the quantum computers?
Not directly. Nothing, let me say, nothing that we discover at the LHC affects quantum computing. It's a different line of technology, that I can say. But I can only say one thing: quantum computing technology is pursued at CERN. So CERN has a budget for it. It's not mainstream yet, but people are working on it at CERN. There's like a piece in part in the organization which is dedicated to understanding this technology and figuring out how to use it. Well, unfortunately, nothing from our experiments directly contributes to it.
Okay. Thank you very much for your answer. And last question. Could you tell, please, if there are any sustainable proofs to Big Bang Theory, or is it just a pure imagination? Because to my view, it doesn't make sense at all.
Well, then I'll have to disappoint you. Yes, of course, the Big Bang Theory, not in all detail, but conceptually, is observationally supported.
May I ask a question about that, if I continue?
Yeah, sure.
It will be again, or there was just one big how can I say that? I'm sorry about it. It's just one bang in the history.
Okay.
Or, as I said, it will process about continuously.
Okay, so that we don't know.
We don't know. Okay.
That one we don't know. Indeed. So right. Let me go back a little bit more. So the Big Bang, as I described in the beginning, yes, all of the universe was squeezed in one place, and then it kind of expanded. Well, there was a bang, and then an expansion, and then this universe started expanding and cooling down. Particles started forming, etc., etc., etc. So this idea, and not all of its details, but the idea, as I said, is observationally supported by all sorts of different experiments. So the biggest support, of course, came in 1960s when people observed the cosmic microwave radiation background. So there's this background in the universe. It's about 3 Kelvin. It's just, again, like a field of energy that we can observe. And the calculations were made that if there was a Big Bang, there should be some relic energy in our universe today That's just around 3 Kelvin. So theorists were predicting it, and experimentalists actually accidentally found this this thing. Actually, well, I don't know. You guys are, well, the kids here, they are probably not old enough to know the old televisions. When you don't see a channel, there is this black and white kind of noise in the TV. That's that radiation, actually, that we see. Anyway, yeah, so that's a very big proof, because it really coincides with the calculations of the Big Bang theory. Now, there are, of course, other proofs that come from more later satellite experiments like WMAP or Planck. So they are able to map the universe. They are able to make a big map of the energy distribution in the whole universe by surveying the universe. And these are all really consistent with the Big Bang experimentally. Now, coming to what happens in our universe, this really depends on how much matter, ordinary matter, how much dark matter, and how much dark energy we have, because it's a matter of balance. Well, the universe is expanding like a balloon, expanding, expanding, expanding. So depending on how much air you blow in the balloon, right, either it will explode, the balloon, or it will stop at some point because you get tired, or I don't know, then maybe there's a hole somewhere, the balloon will start shrinking. So the answer really depends on us knowing how much dark matter and how much dark energy there is in the universe. And we can only measure this indirectly, not very directly, and not very precise. So far, according to the latest measurements, it's somewhere in between the universe continuing to expand with the same speed and continuing to expand in an accelerated way. But yeah, that's what the latest data is supporting. So it's not going to go back on itself and then we have a new Big Bang. But you don't know. When we make better experiments, maybe this changes.
So we have to stop the waiting then, right?
Yeah, so but there's no problem now in our lifetime. We can enjoy ourselves still.
Dear professor, of course, that was a joke. We are really happy to see you in there, and we are really happy to joining you as an INTOC member from today. Thank you very much. We are really feel honored to have you today. Thank you very much.
Okay.
Thank you very much for today.
Okay, I thank you again for inviting me. I hope, your program continues successfully, and well, until next time.
Thank you very much, dear professor.
Bye-bye, everyone. Have a nice week.
Thank you very much.
Thank you, dear Sezen Sekmen, for your contribution. Thank you. You give your valuable time to us. We are so happy to listen you. It was so impressive and so clear and slice and topic also for us. Thank you for your contribution also to our minds.
I'm glad it was helpful. Okay. Bye-bye, everyone. Have a nice day.
Bye-bye.
Have a nice day, professor. Okay, before quitting, we have an announcement for you. The INTOC is growing day by day, and now we have an announcement about INTOC competition. INTOC competition. First, we have warm greetings from the INTOC Global from these organization members. To organization members. INTOC has been managed and supported by effective and international educators and academicians originated from prestigious universities and institutions such as MIT, Stanford, CERN, Koç, Sabancı, and Hacettepe universities. We think that by providing new insights and solutions, we will strengthen the bridges of the science in the world by communicating with valuable organizations. As a community that grows with this experience, we are honored to announce our international science project competitions. The competition will be held on 29 May and in the June, and we are waiting the participations. For more information, www.intocglobal.org/courses. Thank you very much. There was a lot of course,